So in this final part of the lecture, I will solve the Cooper problem, which is a problem of weakly attractive electrons near the Fermi surface that form pairs, so-called Cooper pairs, bound states of two electrons. And as we discussed, these Cooper pairs, at low temperatures, they both condense into Bose-Einstein condensate, which becomes superfluid, and this is this amazing state that we know as superconductor. I should mention that, as we will see, actually the solution to the Cooper problem will involve essentially the same method we used in the first lecture this week in the context of single particle quantum mechanics. So it's going to be actually very simple, technically very simple solution for a Nobel Prize winning work anyway. So it's not trivial, but you know, this is a very important work. So here I'm actually showing the title of the original paper by Leon Cooper. So this work of Cooper eventually has progressed, has developed into a much more sophisticated theory, which is the Bardeen-Cooper-Schiffer theory of superconductivity, or so-called BCS theory. So, and this BCS theory has been the cornerstone of the theory of superconductivity for many, many years. And frankly, there is nothing better on the market in some sense. So this BCS theory describes very well most conventional superconductors, and it provides some understanding also in the physics of unconventional superconductors, although they're such as the high temperature superconductors, for example, although there the understanding is not complete. Now, as I've shown many times already citations for various Nobel Prizes, and I discussed briefly a number of Nobel Prize winning works, and I should admit that in most of these cases I had to sort of simplify things enormously when I was providing explanations, sort of dumb it down to some degree. So here, well, I'm not going to discuss BCS theory. This is a very complicated theory, but the paper of Cooper is actually very, very simple. So the original paper which started it all is very simple, and we will be able to understand essentially its main message and the derivation. Now, but before going into this derivation, let me discuss the origin of this attractive interaction. So I basically, what I want to solve again is a problem of electrons interacting by an attractive potential. But where exactly it's coming from? So this is actually a very complicated and tricky question. And well, in some sense, the mystery of, let's say, high temperature superconductivity is in that we don't really know where this sort of glue, this attractive interaction might be coming from. So the origin of electron attraction in conventional superconductors is also far from obvious, actually. So, but there was a breakthrough paper back in the beginning of the 50s. So I'm showing here the title of this paper, Superconductivity of Isotopes of Mercury. And to appreciate the importance of this paper, let me just remind you the basic picture of what a metal is. So, well, if you have a metallic system, well, a solid system, so the reason it's a solid is because the ions form a crystal lattice. So they're positioned in space in a regular fashion. So I'm just drawing here, for the sake of simplicity, a square lattice in 2D, but in reality it could be a more complicated three-dimensional lattice. And you should think about having positive ions sitting here in these sides, on this lattice sides. And this lattice is a sort of elastic, well, it's a rigid object, but it can have oscillations, waves running through it. And we're going to discuss it a little bit in a few weeks. And so these oscillations of the lattice are called phonons. Now, electrons in the metal are moving around, they're free to move around, but they move around in the on the background of this lattice. So these red guys here are electrons, okay? And so this is pretty much what, well, a spherical cow model, a simplified, oversimplified model of a metallic solid. Now, so this paper, what this paper has achieved is that it looked at different isotopes of mercury, which is a superconductor. And let me remind you that isotopes are essentially different versions of the same chemical elements. Basically, everything is the same for different isotopes apart from the number of neutrons in each ion sitting on the lattice side. So, but basically, so different isotopes means that everything is the same, but the only difference is the mass of these objects on the lattice sides, which, well, naively shouldn't affect too much superconductivity, because clearly superconductivity is coming from whatever electrons are doing, and it shouldn't have much to do with the lattice, right? So, because these guys are actually, well, they can oscillate a little bit near their equilibrium positions, but they cannot conduct electricity. So, but it turned out, and this is really the main message of the paper, that the transition temperature into the superconductor, the temperature at which the resistivity drops exactly to zero, depended very strongly on the mass of these guys, okay? So, and the heavier the ions, the lower was the transition temperature. So here maybe it's hard to see, so there are a few points. So this says average mass number, and this says transition temperature. So this is basically, let me write it, Tc, and this is the mass of these ions on lattice size, okay? And so this was a very clear-cut trend, and it was a smoking gun of that superconductivity had something to do with interactions between the electrons and the crystal lattice. So, and a little later, people realized that what actually happens is that these electrons moving around, they whenever the electron passes through a region in a lattice, so essentially because electron is negatively charged and the ions sitting on lattice sides are positively charged, so this electron polarizes the lattice, okay, so locally, and it takes some time for the lattice sort of to relax back. And then if a second electron comes in, so let's say I have here now this guy goes away and there is a second electron which comes in into the same region, so this second electron is attracted in some sense to this region, and this results in an effective correlation, effective phonon-mediated attraction between the electrons. So it's a very tricky business. So if you don't understand it, well, don't be surprised. I don't understand it either, actually. So, but that's how it works. So we'll have to, just accept this fact. So that what happens is that electrons, in some sense, they exchange waves, elastic waves, which are called phonons, and this leads to effective attraction. Well, and by the way, for the model, for the actual solution I'm going to present, the origin of the attraction doesn't matter that much. It will be just some attraction, some constant, minus V naught, but it's good to know the physics behind it. For the actual calculation, we'll need a specific mathematical model of this electron-electron attraction, and the true interaction is actually quite complicated. But so here I will present what I call a spherical Cow model of this phonon-mediated attraction between electrons, which I should say actually is used commonly even in research papers, so it works perfectly well. And even though we know how to write the true model, which would involve all the complications of the theory, so the results, the outcomes of the simplified model and the more complicated model are pretty close to each other. So there is really no reason for us to complicate things. So in any case, so what we're talking about is that, again, electrons moving around in the presence of a crystal lattice, they exchange waves running through the lattice, these phonons. And so this diagram is an example of a Feynman-like diagram which shows this this kind of exchange. And in any process like this, we must satisfy basic conservation laws. And in particular, we must ensure that both energy and momentum are conserved. So, therefore, what's important here in understanding the structure of this interaction is the typical energies involved in such processes. So what we know, what we already discussed, is the typical energy of the electrons in the metal. So, and this typical energy, I denote it as E sub f, the Fermi energy, divided by the Boltzmann constant, sort of to convert it into a more familiar temperature units. So the corresponding typical sort of temperature of electrons is going to be about 10,000 Kelvin. So these guys, which actually the main players of the theory, have the energy which is associated with this temperature scale. Now, it turns out that the phonons, it's not obvious from the previous discussion, it's not something we can derive, I'm just sort of giving you an experimental fact, is that if the typical energy of the phonons, which I will call as h times omega dBi, so-called dBi frequency divided by the Boltzmann constant, so when converted into temperature is about 400 Kelvin, a few hundred Kelvin, so which is 2 orders of magnitude smaller than the energy of the electrons. So what we should think about is that these phonons actually being exchanged by the electrons have energy which is much smaller than the energy, the electron energy itself. And this puts certain constraints on the possible momenta and energies of the electrons that may experience this sort of a process. And the simplest sort of version of the interaction which takes this into account is presented here. So this is an equation for an interaction, momentum-dependent interaction between the two electrons, V of p. And what it tells us is that the two electrons attract each other in this language if they're located in a narrow shell near the Fermi surface, and the width of the shell is of the order of this phonon energy. So basically, if two electrons can exchange phonons, they do so, and this results in the attraction, which is manifested here through this negative coefficient, and V naught is some constant. And if two electrons are located beyond this narrow region, so then they don't have a mechanism to attract each other, and their interaction therefore is 0. So if we look just at the upper part, so V of p is equal to minus V0, so this would correspond to essentially a local attraction in real space. So this is something we actually saw in lecture number 5 for the delta potential. So this is the kind of problem we discussed already. And but however, then we were talking about one particle in a quantum well. So now we're talking about two particles, two excitations interacting with each other via this potential. But per the results of the previous segment in this lecture, we know that the two-particle problem in quantum mechanics is to a large degree equivalent to a single particle quantum mechanical problems. And as we discussed in the previous video, the only difference between the single particle problem and a potential V of r and two-particle problem of two particles interacting by the same potential is that in the latter we will get the reduced mass instead of the mass of each individual particle. And in the case of two identical electrons, the reduced mass is equal to m over 2, so we have simply this Schrödinger equation. And here I write it first in real space, sort of, but keeping in mind that there are in fact additional constraints on the interaction. So if we follow the same route that we did in lecture number 5 and do Fourier transform, so we can write this equation in this form. So delta of r acting on psi of r picks up psi of 0, and so here I'm going to have this integral over all momenta, but basically a way to introduce constraints on the potential that we just discussed would be to limit the integration over momentum here by only momenta that appear in the vicinity of the Fermi surface, so that the possibility of phonon exchange exists. And so this equation, essentially these two equations with the appropriate sort of caveats about where the interaction is possible, is exactly the Cooper pairing problem. And as you can see, it's essentially identical mathematically to the kinds of problems we saw in lecture number 5 in single particle quantum mechanics. And so, well, we can follow the same route, but at this stage we may be a little bit surprised by this resemblance, because I mentioned that this eventually the result of this calculation is going to be the appearance of a bound state between the two electrons. But as we discussed, weak attraction in 3 dimensions, and this is a 3-dimensional problem, does not result in a bound state. So a delta function potential in 3D does not have a bound state. However, an interesting thing that happens here is that because electrons that really play a role in this pairing and this interaction with phonons, they exist in the vicinity of this Fermi surface, and this surface is 2-dimensional, this gives rise, in a sense, to reduction of dimensionality. Even though in real space we started with a three-dimensional system, so this effectively, what we're dealing with here has a reduced dimension. And this gives rise to the appearance of a bound state in a very unexpected way. So to see this, we essentially have to repeat exactly the same steps as we did in parts 3 and 4 of lecture number 5. So the only difference here is due to the fact that this energy in the left-hand and the right-hand side that we want to find really consists of two parts. So this is the energy of the electrons that already have a finite energy at the Fermi surface. So remember that we're talking here about these excitations that have the energy of 2 Fermi, and then there is an energy due to the interaction, which we want to be negative. So if this guy delta is negative, it means that we can form a bound state, and by doing so lower the energy. So well, this fact actually makes all the difference. Actually, this is how mathematically the fact that we're dealing with this two-dimensional Fermi surface manifests itself in this equation. Since the remaining calculation follows almost one-to-one that in lecture number 5, and I also present this particular calculation, all the details in additional materials, so you can read through this. So I'm not going to repeat this again in this video. So what I'm going to do, I'm going to just present the final result for this key parameter delta, which again is the energy of the bound state of 2 electrons that form sort of a large molecule, if you want, which is called Cooper pair here. So, and this delta is going to be of the order of minus h omega d. So this is phonon energy, typical phonon energy that we discussed in the previous slide. But the key thing here is that there is multiplied by an exponential of -1, some constant, I'll call it n naught and define it in a second, times v naught. So where n naught is equal to m p Fermi, so this is this threshold momentum divided by 4 pi squared h cubed. So this is just some constant, but what I want to emphasize, well, first of all, there is a solution, which is great. So the electrons indeed can find a way to lower their energy by forming these bosonic Cooper pairs that eventually form the superconductor. But what is not so great is that this small interaction energy appears in the exponential as -1 or v naught. So if v naught is small, then, well, the energy of the bound state, the so-called superconducting gap, is exponentially small, and this is exactly what happens. And those of you who followed all segments in lecture number 5 can recognize this result as a result that we have seen actually in the context of two-dimensional single particle problem. And this reflects this reduction in dimensionality that I mentioned before. So the last two things I'm going to mention in the end is, first of all, this result for delta as a function of v naught is a very unusual function, which we have already seen, but this function again is special because it doesn't have a Taylor expansion. So there is no way one can approach this result by doing so-called perturbation theory. And this may be one of the reasons why it took so long for people to figure out the key to superconductivity, because there was no way to approach it sort of in a perturbative way. And the last thing I'm going to mention is that, well, if we did not have this exponential, if we were to imagine that this delta was of the order of this phonon energy, this would have actually implied that we can get superconductivity at very high temperatures, up to room temperature. So this would have been great. We would have the ability to transport electricity with no losses. So this is really the grand challenge in the field. So how to go beyond this weak coupling, so-called weak coupling pairing model. So how to, first of all, describe the situation where the interactions are strong, and how to enhance, how to get rid of this exponential, essentially. This is a sort of a practical problem that has no solution at the moment.